Hi, and welcome back to Material Strength. Force equals mass multiplied by acceleration. One can deduce from this equation, F equals ma, that if an object is not accelerating, that there is no resultant force acting on the object. If there is no resultant force acting on the object, then the forces must balance each other, and the object is in a state of equilibrium. Going a bit further, if an object is moving at constant velocity, it is not accelerating and therefore is at equilibrium. As discussed previously, tension is the force of stretching an object apart. Similarly, compression is the force of pushing an object or objects together. Tension and compression are easy to understand, but if we talk about a loaded structural member, failure mostly does not occur under these loads. The structural designer will find that failure often occurs in shear or under bending moments. Shear force is a sliding force and acts perpendicularly to the body. Imagine a cantilever beam loaded under a large force on its end. Drawn much exaggerated, the beam wants to bend downwards. If one slices a small section out of the beam, there will be a moment acting either side of the slice. There will be a large tension stress at the top of the slice and a large compression stress at the bottom of the slice. This combination of stresses inside the beam will often cause the first failure and is called the bending moment. There's a handy graphical way to determine the intensity of the shear force and the bending moment in a beam. An engineer will want to know where in the beam the highest stresses are, of course, to choose the right material and the profile for the job. A moment is a rotational force or a torque. When a body is in equilibrium, the sum of all the forces on that body is zero. This is true for both the sum of all linear forces in all directions and the sum of all moments acting on the body. Here are three examples of forces and moments. Let us take a look at a spreader beam for a lifting machine. Please follow in your learner guide. Here we can see the forces acting on the beam. Since the beam is not moving, it is in equilibrium, and the force of the crane is equivalent to the magnitude of the sum of the forces from each of the loads and the beam weight. In the second example, we can see both the forces and moments acting, as Bob holds on to the branch. Remember, a moment is a torque that is a rotating force. In the third example, we can see forces acting at an angle to the reference plane. Look at your workbook at how this is reconciled and the forces are separated based on directions. Example of a simple beam load case, where the beam is supported on either end with hinge connections and has the load in the center. Stress of the system to the allowable stress for the chosen material. Just note that hinged connections means that there are no moments or rotational forces acting on the ends of the beam, as can be seen in the force diagram in your learner guides. First, calculate the forces. Fw is 9,810 newtons by substituting the mass of 1,000 kilograms and the gravitational acceleration of 9.81 meters per second squared downward. We know that the beam is not moving. It is in equilibrium, and therefore the sum of the forces are zero. The weight is evenly distributed as it is positioned in the center, so Fy1 equals Fy2 equals 4,905 newtons upward. Second, draw the shear diagram with distance along the beam as the x-axis. See your learner guide. The shear force acting on the beam is caused by the vertical forces. The shear stress will start at the start of the beam at 0 meters, where Fy1 acts. The value of Fy1 is 4,905 newtons upwards. Therefore, the shear force value will be positive 4,905 newtons. There are no other vertical forces acting on the beam up to 1 meter, where Fw acts in a downward direction. The shear force decreases by 9,810 newtons, the value of Fw. the shear force will decrease from positive 4,905 newtons to negative 4,905 newtons. It will remain at negative 4,905 newtons from 1 meter position until the end of the beam, the 2 meter position, where Fy2 acts on the beam in an upward direction. The shear force will increase by 4,905 newtons from negative 4,905 newtons to 0 newtons. Notice the sum of the forces equals 0, static equilibrium. The bending moment diagram can be calculated directly from the shear force diagram. The shear force is the derivative of the bending moment, or the bending moment is the integral of the shear force. This is very handy because it means that the value of the bending moment will be the area underneath the shear force diagram. This makes perfect sense because a bending moment is a force multiplied by a distance. The value of shear force from 0 to 1 meters is constant. Therefore, the slope of the line of the bending moment diagram will be constant from 0 to 1 meter. The value of the bending moment at 1 meter will be the area underneath the shear force diagram of 4,905 Newton meters. In exactly the same way, the bending moment will decrease from 1 meter to 2 meters by the area of the shear force diagram to a value of 0. Now we can see that the maximum bending moment happens at the center of the beam with a torque of 4,905 Newton meters. Before the engineer can compare stress of the system to the allowable stress for the chosen material, the mechanical design or the shape must be considered. This is described by moment of inertia, which is to resist rotational change or acceleration. So why does the shape affect the stresses on the materials? Take the beam from the example just discussed. The load in the middle of the beam will cause the beam to deflect downwards. If we cut a slice of the beam along lines AA and BB, the top half of the sample will experience a stress in compression. The bottom half of the sample will experience a stress in tension. The line in the middle of the beam, where the bending moment stress is 0, is called the neutral axis of the section. The stress caused by the bending moment is 0 at the neutral axis and increases to the top and the bottom of the beam. This means that a stronger material must be used at the top and the bottom of the beam, that the profile or the shape used must have more material at the top and bottom than in the middle. Consider the shape of an I-beam. A cross-section shows how the material of an I-beam is removed from this neutral axis towards the top and the bottom. Two thick horizontal flanges are separated by a rather thin vertical web. The top and bottom flanges are the parts that experience the most stress and thus contribute the most to the strength of the profile. The moment of inertia is a given value dependent on the profile or the shape. In this example, it is 23.5 times 10 to the minus 6 meters to the fourth. See your learner guides for a reference. The stress in a beam due to the bending moment can be calculated with the following formula, where the stress is equal to the bending moment multiplied by the distance from the neutral axis and divided by the moment of inertia. The maximum bending moment in our early example of 4,905 Newton meters. The profile of our beam is a standard I-beam with a moment of inertia equal to 23.5 times 10 to the minus 6 meters to the fourth. The material of the beam is stainless steel grade 316 with an allowable stress of 205 megapascals and a required safety factor of 2. These are determined by building codes. Our chosen profile is symmetrical. Therefore, the neutral axis will be half of the height of the profile, so the value of C is 101.5 millimeters. The calculated stress using the formula is therefore 21.2 megapascals. From the allowable tensile stress table in the learner guides on page 10, stainless steel is 205 megapascals. The actual safety factor may be calculated and is far greater than the required safety factor of 2. Therefore, the stress in the beam is well within limits for the chosen material of stainless steel and the profile of the I-beam. Remember that there are other factors to consider when choosing material, such as temperature, corrosion, and even vibration.